How can two droplets that never touch still communicate and influence each other's behavior? Let's explore the fascinating physics of hydrodynamic interactions. Imagine two droplets in a microchannel. They never touch, yet they communicate through the surrounding fluid, exchanging information about their presence and motion. First, let's understand the physical environment where this communication happens. We have a microchannel, typically tens to hundreds of micrometers wide, with droplets flowing in a continuous phase fluid. The key question is, what happens to the fluid surrounding each droplet as it moves? As a droplet moves, it displaces the surrounding fluid, creating a flow field that extends far beyond the droplet its. To understand the physics, we need to determine the Reynolds number of our system. The Reynolds number is defined as density times velocity times length scale divided by viscosity. Let's perform a back-of-envelope calculation for a typical microfluidic droplet. The fluid density is approximately 1,000 kilograms per cubic meter. Typical droplet velocity is about 1 millimeter per second. The droplet diameter is roughly 50 micrometers. The dynamic viscosity is about 10 to the minus 3 Pascal seconds. Plugging in these numbers, we get a Reynolds number of approximately 0.05. This is very small. Such a low Reynolds number means we're in the Stokes flow regime, where viscous forces completely dominate over inertia. In Stokes flow, the velocity field forms smooth, reversible patterns. There's no turbulence, just laminar flow everywhere. Now let's examine how a droplet creates pressure perturbations in the surrounding fluid. In Stokes flow with incompressible fluid, pressure satisfies Laplace's equation, del squared P equals 0. A moving droplet creates a pressure field around it. High pressure builds up in front, low pressure behind, and these pressure perturbations decay slowly with distance. Here's a critical insight. In a confined microchannel, pressure perturbations decay as 1 over r, not 1 over r squared as in unbounded flow. The pressure at distance r scales as 1 over r in quasi-two-dimensional confinement. You might ask, why does confinement change the pressure decay rate? The walls constrain flow to essentially 2 dimensions. Fluid can't escape in the third direction, so pressure effects propagate further downstream. Let's visualize the velocity field that a droplet creates in the continuous phase. The velocity field shows fluid being pushed aside by the droplet and circulating around it. This creates a dipolar flow pattern. The induced velocity at distance r scales as the force divided by viscosity times r. This velocity field is the communication channel between droplets. One droplet's motion alters the flow, which then affects the second droplet. The leading droplet modifies the flow field, which then affects how the trailing droplet moves. This is bidirectional communication through the fluid. Now let's analyze the actual interaction forces between two droplets. Consider two droplets separated by distance d in a microchannel. The separation distance d determines the strength of their hydrodynamic interaction. The interaction force scales as viscosity times velocity times droplet radius squared divided by separation distance squared. An important question: what happens as droplets get closer together? As separation decreases, the interaction force increases dramatically, following an inverse square law. This graph shows how interaction force diverges as droplets approach each other. The closer they get, the stronger they interact. One major consequence of hydrodynamic interaction is that droplets modify each other's speed. The trailing droplet typically moves faster than it would if isolated, because it's pulled along by the leading droplet's wake. The trailing droplet experiences a reduced drag because it sits in the low-pressure wake of the leader, so it accelerates. The speed modification scales as droplet radius squared over separation squared times the base velocity. Let's do a quick calculation. For a 10 micrometer droplet at 100 micrometer separation, the fractional speed change is about 1%, small but measurable in experiments. Hydrodynamic interactions also control the spacing between droplets and determine whether spacing is stable. A crucial question: will droplets maintain constant spacing, or will they eventually collide or separate indefinitely? The interaction can be attractive, pulling droplets together, or repulsive, pushing them apart, depending on the detailed flow conditions. The rate of change of separation equals the velocity difference between trailing and leading droplets. If the trailing droplet is faster, spacing decreases and droplets approach each other. Stable spacing requires a feedback mechanism where closer droplets repel and distant ones attract, creating an equilibrium. This graph shows the rate of spacing change versus separation. Where the curve crosses zero with negative slope, we have stable equilibrium spacing. Beyond translation, hydrodynamic interactions cause droplet deformation. The pressure field created by neighboring droplets can compress or stretch a droplet shape. The middle droplet experiences asymmetric pressure from its neighbors, causing it to deform from a sphere into an elongated shape. The capillary number, viscosity times velocity over surface tension, determines deformation magnitude. For small capillary numbers, surface tension dominates and deformation remains small. Typical fractional deformations are 1 to 10% in microfluidic systems. When droplets get very close, lubrication theory describes the thin film between them. As droplets approach, a thin film of continuous phase fluid is trapped between them. The film thickness H determines drainage rate. The pressure in the thin film scales as viscosity times velocity over film thickness squared. An interesting question: can droplets ever actually touch, or does the film always prevent contact? The drainage time scale is viscosity times radius over surface tension. For typical parameters, this is milliseconds to seconds. Surfactants or surface charges can stabilize the thin film indefinitely, preventing coalescence. The overall flow rate in the channel dramatically affects droplet interactions. Higher flow rates Q mean faster velocities, stronger interactions, and more dramatic communication between droplets. Velocity scales as flow rate divided by channel width times height. Increasing the flow rate increases all hydrodynamic interaction effects proportionally. Interaction force scales linearly with flow rate, making Q a powerful control parameter. The channel geometry profoundly affects how droplets communicate. In narrow channels, confinement is strong and interactions are long-range. In wide channels, interactions decay faster and behave more like unbounded flow. The confinement parameter lambda is droplet radius over channel width. Large lambda means strong confinement, where channel walls dominate the physics. When lambda exceeds 0.5, we're in the strong confinement regime with dramatically altered interactions. When many droplets flow together, collective effects emerge that go beyond pairwise interactions. A train of many droplets creates a collective flow field. Each droplet feels the combined influence of all others. Droplets in the center of a train experience different forces than those at the edges, leading to position-dependent behavior. The force on droplet N is the sum of pairwise forces from all other droplets M. This diagram shows how force varies with position in the train. Center droplets experience maximum collective effects. Perhaps most surprisingly, hydrodynamic interactions can cause droplets to split without any physical contact. A droplet can be deformed by hydrodynamic stress, stretched into a dumbbell shape, and eventually pinch off into two smaller droplets. There's a critical capillary number around 0.5, above which splitting becomes favorable. The neck region thins due to strong pressure gradients and eventually breaks, creating two daughter droplets. How fast does the neck break once it starts thinning? The breakup time scales as viscosity times minimum neck thickness over surface tension. This is typically microseconds. We can understand droplet communication through an energy landscape perspective. The interaction energy between droplets has minima corresponding to stable configurations and maxima representing barriers. Total energy includes hydrodynamic work and surface energy contributions. Droplets naturally evolve toward configurations that minimize total energy, subject to flow constraints. Different physical processes operate on different timescales, creating a hierarchy of responses. The convective timescale is channel length over velocity. This is how long droplets take to traverse the channel. The viscous diffusion timescale is density times radius squared over viscosity. The capillary timescale is viscosity times radius over surface tension, governing shape relaxation. In typical microfluidics, The capillary time is much shorter than convection time, so droplets quickly relax to equilibrium shapes. This timeline shows the hierarchy of timescales, from fastest capillary relaxation to slowest convective transport. How do we observe these hydrodynamic communications? Experimentally. High-speed imaging directly reveals velocity fluctuations and spacing variations between droplets. The middle droplet experiences asymmetric pressure from its neighbors, causing it to deform from a sphere into an elongated shape. In conclusion, droplet communication through hydrodynamic interactions is a rich and complex phenomenon. Hydrodynamic forces and torques dominate the behavior of microfluidic droplets, enabling a wide range of applications.